Richard Smalley received his PhD from Princeton in '73. He came to Rice University in 1976. He was named the Gene and Norman Hackerman Chair in Chemistry in 1982. He went on to be elected to the National Academy of Sciences, the 1992 E.O. Lawrence Award of the U.S. Department of Energy, other awards culminating in 1996 in the Nobel Prize in Chemistry. And that particular Nobel Award was for something that also has an Aspen connection, for the Buckminster fullerenes, which was named in part after Bucky Fuller and his work with geodesics. Bucky, you may know, came to Aspen and had seminars at the Aspen Institute as well as at the Windstar Foundation. Tonight's talk is titled Our Energy Challenge, and I think it will take a broad view of what we're facing, the challenges that we're facing in this energy topic. We have generous support to make this meeting possible from the Department of Energy, from NASA, and also from the Hewlett Foundation out in California. So please join me in welcoming Dr. Smalley.
Thank you. I appreciate the opportunity to talk, particularly at this place where there is such a superb group of scientists, engineers, economists, and so forth looking at energy and the climatic implications of it, and particularly what we can do about it. This is not my day job, talking about energy. In fact, it's only been about a year that I have really studied this issue to any extent at all. It was triggered last year about this time when I was invited to testify to the Science Committee of the House in a hearing on the future directions of the Office of Science of the Department of Energy. And I jumped at the chance, and having testified earlier in the House, I knew what a great opportunity it is when you prepare your 5-minute written remarks, because that you get to pass it around to people and they get to think about it. So I took a week off to prepare for this, and it occurred to me that the principal objective of the Office of Science in the future ought to be energy, and so I took a week to take a look and see how we're doing on energy, and I was really quite struck by what I was finding. Even in a couple of days, I was going into this thinking that we had another 30 years before this became a big issue. But after a few days looking into it, it became quite clear to me that it's not at all obvious that we'll have anywhere near that period of time. And so I spent a week doing this, and I composed this document, and there happened to be a meeting of the BSAC, the Basic Energy Sciences Advisory Committee, that I'd been serving on for several years before, just the next week, and I was able to iterate with the people of the Department of Energy and refine my arguments. And I ended up with actually a very strong statement that when I wrote it, I felt this is probably a little bit over the edge, but I think it's true. It's the logic of the argument, so I'll just make it. I mean, one of the great virtues of having a Nobel Prize and working in a private university with tenure is you can say anything. So I figured, how bad could this be? I'll just say it. And I was struck on the day that I said it, not only the people sitting there, but the staffers and the few members of Congress I talked to. They didn't think it was that ridiculous at all. And the next day when I talked to other people, they didn't think it was that ridiculous. I was calling for a bold increase in the funding of frontier research in this country. Going up, adding additional $1 billion to this effort in FY04 and ramping up to about $10 billion a year and holding it there until we had the problem solved. And I thought, well, having experience in writing proposals for federal grants, you overshoot a little bit knowing you'll have to come back a bit. But in fact, in subsequent conversations, as day passed after day, I didn't find people that thought it was ridiculous at all. So this was about early July last year, and so I continued doing this sort of on the side, and in a typical month I'll give 5 or 6 talks about buckyballs or bucky tubes or bucky things, nano something, and I had a whole bunch of talks set up. So I decided that I would make use of them and do a little audience participation experiment with these at the beginning. I said, I promise I'm going to talk about the nano that I promised to, but first I just want to do a little experiment. What would happen if I put up a PowerPoint slide that just had the numbers 1 through 10, nothing after them, and at the title of it, it said, humanity's top 10 problems for the next 50 years. I'm interested, just on the spur of the moment, what you would think as an audience. And so people would think for about a minute. I thought it would be kind of a dead response, but no, when once people got into it, you started getting a whole series of problems. And I said, well, as you're suggesting these, I'll warn you in advance, I have 3 hypotheses that I want to test on your answers, but I won't tell you what they are until you give me the answers, because I don't want to bias it. So the 10 problems on the list here are typical. In fact, the top 7 were volunteered on the spur of the moment by every audience that I've done this with, 12 audiences. And after you've done it 12 times, people know that you're going to do it, so it's no longer really a fair test. But there's actually a remarkable degree of consensus on this, and the remaining 3 of the 10 were members of actually a fairly small set of others, that are not more than 6 or 7 others. And so I've chosen these, the top 7 because they're always suggested, and the bottom 3 because sort of my personal guess of what's most important. I said, okay, well, my hypothesis was that if you ask any audience, any group of people, 2 or more, whenever they're gathered together, you ask them this question. Now, at least since 9/11, I'll bet you that energy always appears on that list someplace. And so far, my experience has been that's always the case. The second hypothesis is no matter in what order it was suggested, if you move it to the top of the list, and here I would display my great skill of PowerPoint and being able to move it up there, and you imagine that through some miracle, that problem has now been just solved. So there is now abundant energy available at low enough cost to do whatever is necessary all around the world. It's just solved, and it's clean, renewable, problem's gone away. The hypothesis is if you lived in a world where that was true for energy, you would find that now you can see paths to answers for at least 5 of the remaining 9 problems on the list. Whereas if without an answer to the energy problem, it was hard to imagine how you would solve these other problems. So a tremendous cooperativity. And so we would go through the list. It was sort of a group revelation experiment to see just to what extent that's true. And I have to tell you, I've organized them sort of in the order of their importance and the immediacy of their energy impact. And water is a great example. Most people who have really thought about humanity's problem for this next century agree that if energy is the number 1 problem, water is certainly number 2. We may very well have major wars fought in this century over water. And it's a great example of a problem that's dependent on energy. And water is a very brutal problem. I mean, either you've got water or you don't. If you haven't got it, you've got to get it. You can't calculate your way out of it. You can't just imagine you've got water. You've got to have it. Luckily, we live on a planet with a lot of water. But it has salt in it, usually, and it's often thousands of miles away from where we need it. Well, we can take the salt out. You can think of some fancy nano membrane of the future, or you can just boil the water. That works pretty good. But you can take the water, the salt out of the water. It takes energy, massive amount of energy when you consider the amount of water you need to handle not only drinking water for humans, but agriculture and farming and so forth around the world for now 6 billion people and soon to be 9 to 10 billion people by the middle of the century. if you have energy in the abundance and the low cost that I'm talking about, and if it doesn't carry its own environmental burden with it that keeps you from otherwise using it, you could solve the water problem. You just solve it. On the other hand, if you haven't solved the energy problem, you can't solve the water problem. You're just never going to do it. Food, my answer to food is seawater. C number 2, seawater. Now, granted, there's more complexity in raising food than just water. You have to have reasonable soil, and you have to have fertilizer and so forth. Water is the key thing. The other things I just mentioned are also critically dependent on energy. If you solve the energy problem, you solve the water problem, you can solve the food problem for 10 billion people. Without energy, it ain't clear how you solve this. How do you get 10 billion people to be able to live like the people in Aspen without somehow solving that problem? And they all want to. And the more they find out about how beautiful this place is, the more they're going to want to do it. And in an information age, they're going to know. Fourth problem on the list, environment. I think it's just simply flat out true that the vast majority of our environmental problems are either directly a result of the energy sources we use and the way we use it, or there are problems that we could solve if we had clean energy in the abundance and low cost to clean up. So if you want to solve, if you really care about the environment problem, saving tin cans is not good enough. You got to solve the energy problem at this mass scale for 10 billion people on the planet. Poverty, that there is no single more determining factor in the prosperity of society than the availability and economic availability of their energy supply. As I'm sure the vast majority of you know, we have a greater imbalance between the rich and the poor living on this planet than we ever have in recorded history. Jeremy Rifkin, in a talk he gave at Rice, made a statement that you take the top 350 richest people on the planet. You could fit them in the room that we were in then. You couldn't fit them in this room. They earn more than the bottom 1/3 of humanity. I mean, that incredible imbalance of riches. You're not going to solve that problem without solving the energy problem. And vast energy, clean, low cost. If you don't have it low cost, you haven't solved the problem. Terrorism and war, certainly in this century, it was even true in the last century, that energy was a dominant factor in most of the wars that were fought. Certainly in this century, if we don't solve the energy problem. And the other ones that are so immediately related to energy, they're almost a corollary of the energy problem. That probably is going to be the basis of the political instability and what ends up being the driver for continual terrorism and war. And I think I've already made my point. I have other places to go, but it's just really striking the extent to which it's true that energy has this pivotal ability to help not only many of the other problems, but in many cases actually the top problems facing humanity as a whole. The third hypothesis is that you take any other of these problems that is suggested in the top 10 and move it to the top of the list. You will find that there's not anywhere near the cooperative effect on the remaining 5 as energy. Now, if there's an exception to that, it's number 10, it's population. If you move it to the top and imagine it's solved, then yeah, probably with the current technology, we could get through the rest. But what is the level of population that would solve that problem? Well, at most, it's 1 billion people. And well, we have 6.3, so what did you have in mind to do with the other 5.3 billion people on the planet? Interestingly, to me, really fascinating, as I give these talks afterwards, we're sitting around and talking just in the hallway afterwards, and I say, well, so what do you think? And they'll say, well, I don't think we're going to have anywhere near as many people by the middle of the century as you're extrapolating. And the typical extrapolation is about 9 to 10 billion people now. And I said, oh, really? That's interesting. How many do you think there's going to be? He said, well, if it's possible we could be 1 billion. Do you realize that there's never been a time in human history when population has ever dropped by even a half, let alone a factor of 5? I mean, this would be even the apocalypse would not be enough to get you down to this level. I think it's just fascinating that I hear this so often. It must be a deep aspect of human nature. And I think I know what it is. I mean, when you're face, particularly when you're young, with a problem that's so vast you just can't imagine any way to solve it. You get into a mode where you're waiting for somebody else. Some big event will solve it for you. And it reminds me when I was in grade school in Kansas City, Missouri, public grade school. I hated school. I hate it now. And it was in the early to mid-50s, and I can remember going to sleep at night praying for thermonuclear war so that I wouldn't have to go to school the next day and admit that I hadn't done my homework. Well, you know, I think it's just a typical immature reaction to really huge problems. In the real world, though, the sun does come up the next day. You do have to go to school, and you do have to tell them that you didn't do your homework. In our real world, by the middle of the century, there is going to be somewhere between 7 and 12 billion people on this planet. And either we found a way of making it possible for a reasonable fraction, and really it ought to be all of them, to live a fulfilled life, or we're going to have to pay the consequences of it. And so I don't see the population as a solution. It certainly is pivotal, but there's not much we can do about it. Energy is unique because it has this tremendous ability to affect other problems, and we can do something about it. You know, forgive me for being sexist, but it's kind of a guy thing. You know, we're going to go and techno-fix this problem. And we can technologically fix this problem. And that's why I keep on being in this, because I'm a physicist and a chemist, and I know that community pretty well. And if there's going to be some answer on a relevant timescale to affect this industry by 2050, I ought to be able to, you know, talk to people that are going to be saying some of the words will be part of that answer. So it seems to me that going through this exercise, and I encourage you to do this with whatever group, go to your church group or your civic community or, you know, whatever group you want to test it with, and go through this exercise. I think that you'll end up, as I have each time, without trying to bias it, with the simple conclusion that if you had to pick one issue that is more important than any other single issue for humanity on this planet, it would be energy. And I haven't really heard a significant argument that pushes back from that. Well, there's tremendous power in that. If we can all agree what the biggest single problem is, we're a good part of the way to answering it. Well, okay, so what is the magnitude of this problem? This is a quantitative issue, as you all know. Energy right now is the biggest enterprise of humanity. It's roughly $3 trillion a year, dollar volume, in direct energy or the industries that are very close to it and affected by that enterprise. $3 trillion. The second biggest enterprise, these are estimates by Matt Simmons, an investment banker in Houston that's been in the energy business for 25, 30 years. Second biggest enterprise in humanity is agriculture at about 1.3 trillion, about half of energy. And third is defense. All of the military all over the world is about 0.7 trillion. So energy just hands down the biggest enterprise around. And you all know what probably the distribution of energy that we're using right now. By the end of 2003, if we don't go into worldwide recession, the total energy usage per day is going to be somewhere between 13 and 14 terawatts, or in the energy units that we like in Houston, Texas, 210 million barrels of oil equivalent per day is what we use around the world. Most of it is fossil energy. A significant piece is fission with the current generation of light water reactors, about 400 of them. Quite a significant piece of biomass being burned. A lot of that you see there is by the undeveloped world burning vegetation just to cook the evening meal. A pretty significant amount of hydroelectric, and then this teensy little thing you can hardly see was all of solar, wind, and geothermal. And in fact, you wouldn't see any color in there in that bar from where you're sitting, were it not for the fact that I added in geothermal from places like the geysers in San Francisco and so forth. The solar and wind is too tiny to actually see on this chart. So that's where we are today. By the middle of the century, 2050, there's all sorts of guesses on how much energy we'll need. The midline guess is at least twice of what we have now. And so this square is about twice the area of the previous one. And here's a stab at what the distribution of where that energy might come from, is where it's most likely. When you internalize just what the magnitude of the energy business is, and then you realize that when you go off looking for a way to do that in the middle of the century 2 times over, there aren't actually a lot of possibilities that can give you energy at that scale. And the place where the big energy is to be found, and particularly the place that with big energy is to be found that has a chance of being environmentally clean, is in this one section here that right now really doesn't matter. It's just not a player. In Houston, Texas, when you talk to people about solar power, they just smile at you. You know, that's not real energy. That's some sort of yuppie little environmentalist thing on top of a traffic light way the hell on out. That's not real energy. And yet, by the middle of the century, in order to be responsive to this challenge, it's got to pick up a big piece of that energy. And what I put in here, 50%, Shell's midline scenario for 2050 is at 30%. BP is not so different from that. This isn't all that dramatic a thing. I've actually shown a lot of fission and fusion here that's probably never going to happen because we can't get it cheap enough. This is sort of an optimistic scenario. The reason I put this up is to make one point. Here's the biggest enterprise of humanity. And over the next 50 years, it's going to be revolutionized in order to solve this problem. That's not easy to do. It takes, Lord knows how many trillions of dollars to do it, decades to put it in, even after you have the technology to begin with. So 2050 seems like it's so far out that we don't need to worry about it until you realize that the technology to do this is not with us now. We don't have the fundamental enabling technologies to make that happen. And if we're going to make the scientific discoveries and the engineering breakthroughs that make it possible to not only do this but get rich at the same time, we're going to have to do it over this generation. You know, the next 10, 15 years, otherwise it's going to be too late. We're never going to make it. In the last century, there's no question oil was the basis of energy prosperity of the world. It was the basis of prosperity. I mean, particularly now that we're looking for a new portable energy source to replace gasoline and looking at hydrogen, and now you begin to appreciate just how magnificent oil was. Gasoline is God's most poetic answer to the question of how you put hydrogens around carbon and get some liquid that fills the volume of the tank and it's volatile enough to use an internal combustion engine but not too volatile. That's perfect. That's it. That's poetry. It's the best you're ever going to get. I love those gasoline molecules. Were it not for the fact that they come from somebody else's desert and that we have this emerging CO2 problem, it would be by far, I mean, water and CO2 perfectly fine. And here, if you read the story of oil, there's this magnificent book called The Prize by Daniel Yergin, published in '93. He actually got the Pulitzer Prize. It's the story of oil for the last 150 years. In many ways, it's the story of world history, seen through the eyes of oil. It's like watching a soap opera, and when you finally realize who's sleeping with who that episode, now you begin to understand what's going on. If you look at world history through the eyes of oil, you will really understand a lot of what really was driving things. So here's this most poetic, beautiful answer to portable energy, and it came self-propelled out of the ground. I mean, people just got crazy rich. You know, particularly when we hit Spindletop, we had more oil than we knew what to do with. And up until certainly middle of the century, the United States was the biggest single producer of oil. And we determined the price of oil up into 1970. The Texas Railroad Commission decided effectively what the cost of oil would be because we could just open the taps a little bit more. But right around 1970, the U.S. peaked in its oil production. After that, it wasn't quite so high. And the next little hiccup we had, well, Texas Railroad Commission had already said, go to 100% on your taps. We couldn't open it up anymore. That's where that first oil crisis came from. Saudi Arabia, OPEC could not have done what they did 5 years earlier. Well, if oil continues to be the basis of energy prosperity in this century, it can't be a very prosperous century. Just simply because we don't have as much oil by middle of the century as we've had in the past century, where it did nothing but go up. But plus we've got billions of more people on the planet with economic advancement in their future. There is an issue about just, how long is this oil thing going to last? And there's a lot of controversy on this, but actually not too much controversy by the time you're looking at 2050. This is a projection of worldwide energy, particularly fossil energy, by John Bookhout, who at that time was president of Shell, in talks he gave in the mid-'80s. And when the president of Shell gives a talk, he doesn't just put up any old chart. This is something they looked at and thought about very seriously. And you see here, it has oil and gas peaking somewhere around 2010, 2015, and then heading down on the other side, slowed down a bit by tar and shale oil, additional unconventional oil and gas. Even shows in this slide coal peaking by about mid-century, with some assumptions I haven't bothered to look into why we don't have more coal. Anyway, this was what John Bookhout's and Shell's projection, wasn't it? And in fact, it's not too far off of what you'll see if you actually look into it, at least in my experience. You can find very strong arguments that we may be peaking now, certainly in oil, and maybe even close in gas, even in this year. You can find strong arguments, it might very well be true, that the peaking could be 2025, perhaps even 2030 in the most optimistic scenario. But it's very hard to find people who seriously, with good data, will argue that we haven't peaked by 2050. And it may be that we can find ways of slowing things coming down the other side. But from the standpoint of 2050, if you're still relying on oil as the dominant thing, this is just not a way for the planet to get rich again. And of course, from the viewpoint of 2050, it hardly matters whether you peaked in 2015 or 2003. That's such a slow curve. It really didn't matter very much. Now, but economically, when the peak does happen, that will not be a trivial event in the energy industry, of course, because every subsequent year there will be less oil to fill a market that is going up, and that's the formula for prices to go up. So, okay, enough about the problem. How about the answer? Primary energy. So don't worry about secondary energy. Primary energy, where is it going to come from? Where are you going to get that magnitude of energy? At least twice of what we're using right now. Another 15 terawatts of power, another 200 million barrels of oil equivalent per day, at least. In fact, it is, unless we have vast efficiencies, and it's possible we could have, unless we have vast efficiencies, it's hard to imagine how India and China and sub-Saharan Africa and all of the billions of people involved can come to a reasonable lifestyle at only that level of energy. So where can you get energy at that magnitude? And my experience has been, and I'm still revising this almost every day, but my experience is that actually that's a very simplifying question. You put the terawatt challenge. If you can't get a terawatt from this energy source, let's talk about some energy source, because we have to add up to 10 terawatts or more before we're responsive to this issue. So let's look for terawatts. So in a sense, this past year, for me, has been a search for terawatts. And so there's a group that I believe really belong in the category of too little. Certainly, in my mind, each one of these individually. And I have a very hard time convincing myself that even if you add all of the items under my little list of too little, and you add them all up, that you'll get to enough terawatts. I have been very impressed, particularly in the last 3 weeks, as I have really met the hardcore of the efficiency people who really think we can, and it's very impressive arguments. I find it hard to believe that that is good enough for the planet as a whole, particularly when you consider water. How are we going to solve this water problem for all these people? And yet many of these are magnificent sources, and many of them are having big pushes right now. In the conventional chemical sources, by middle of the century, there's really only two that make sense as being the dominant drivers. One is natural gas and the other is coal. At the magnitudes that we were going to need it by the middle of the century and for the decades after that, we're certainly going to have to do something with that CO2. And so there's the key issue here: can you ever find a way of sticking it away so it doesn't come back at you at the vast magnitude you do, and doing it around the planet? I mean, I assume by 2050 we're not going to have a world police state where we can go around and say, I'm sorry, you have to shut down that power plant because you're leaking CO2. So we've got to have some technology that works economically planet-wide, and you don't do it planet-wide, you might as well not do it at all. And once we find out a way to do that, if it's possible, and it ain't clear, is it going to be cheap enough? And you haven't solved the problem unless you get it low cost. Well, what's left is actually remarkably a small list. It's all fundamentally a nuclear power. And it's either literally fission or fusion, or it's that nuclear reactor under our feet, the spontaneous fission of uranium-238 and thorium, was it 233 isotope that is the one that we have just in natural abundance. That sustains the heat of the core of the Earth and the mantle, so you can go down and you could mine that heat. There's a lot of it there to be mined. Or you take that big reactor out in the sky. Now, there probably are energy sources that will be relevant to humanity that aren't on this list. So I haven't put them on. There's no cold fusion on here. There's no trapped black holes. There's no antimatter. There's no zero-point energy. There's no dark energy, whatever the heck that is. And maybe we will find ways of harnessing it, but in the relevant time, we just haven't got a lot of time. So I suspect the answer, to the extent there is one for us on this planet, it's on this list. So I don't really, in Aspen, Colorado, to this audience, need to make this point, but I do often need to make it in Houston, that solar energy is not just this yuppie thing for solar cells. It is a serious nuclear reactor. I mean, this is a SOHO satellite that just stares directly at the sun in the extreme ultraviolet, and you can see this. This is not the photosphere. This is a higher temperature plasma above the sun. And by comparison, there's the Earth up here. I mean, this is one massive hydrogen fusion reactor. It's gone through its shakedown trials. It's many billions of years. It's going to be there. It's a terrifying environment to be close to it, even if you get out from the Earth's magnetic field. The solar wind, the proton flux, the radiation can really be a hassle. But down here on the surface of the Earth, we're doing okay. And there is 165,000 terawatts of power hitting the Earth at every moment, day in, day out. And we're only looking for 10 to 20 to 30 terawatts. This has the right scale. We are bathed in energy on this planet, just bathed in it. If we bother to go off the planet, we've got more energy than we could ever possibly think of doing it. Can you imagine that all of civilization is going to crash in this century because we're just holding on to fossil energy and saying, oh, let's learn to be, small and the heck with the poor people, when we're bathed in energy? The only reason we don't have that energy usable for us is we haven't developed the technology to get it harvested cheaply and adapt it to society. I think we can do that. And I think, in fact, there ought to be a new Apollo program, Apollo-level program, bold program to challenge our nation's youth or not so young people to go out there and just solve this problem. I think it's going to be the sun. Maybe it's some other answer. I don't particularly care what answer it is, but I want it solved. A tactical answer. If you were going to do it with solar on the surface of the Earth, with this is a slide from Nate Lewis. I had a fascinating experience this last year learning from people. This is a fascinating issue, particularly at this time. With 10% efficiency, solar cells takes a certain cross-sectional area with normal illumination, considering night and day and clouds and so forth, to garner energy. Here is a picture of actual cross-sectional area in North America and a few continents here. 6 of those boxes of that area, if you add them up together, you will get 20 terawatts of electrical energy, the equivalent of 60 terawatts thermal energy, which, by the way, is a little detail in the energy issue you need to understand. There's thermal watts and there's electrical watts. I owe this insight to David Criswell that's here that has corrected me. 20 terawatts electrical power, plenty for 10 billion people on the planet. This business of population has been going up since the beginning of humanity. Well, actually, in our lifetime, we can now see how we're going to level out. The UN most recent projections, for the first time, their low-level projection actually has us having peaked and heading down the other side by 2050. Terrific news, and it may be the news will even get better as the next few years comes out. If we could handle this problem of the population somewhere between 7 and 10 billion people in this generation, in this relevant time, then I think we have the problem solved. The population develops, 7, 10 billion people, we all are living like people in Aspen. We have a couple kids, we don't have 15, 20, unless we are like Saudi Arabia, where right now the fertility rate per woman is still 6.4 children per woman on average. In Saudi Arabia, it's just flooded in energy. Assuming that doesn't happen, we can solve this problem. We can stabilize population and give the humanity of the planet a reasonable expectation for fulfilled life. And Lord knows what a fulfilled life in 2050 is going to be like. That would be enough. There's plenty of sunlight hitting the earth. Or you can go off the planet. Solar cells sitting out there in space are worth 8, 9 times what they are on the surface of the earth because of the angle of the sun and the night-day thing and clouds, forgetting about dust and the fact you have to go squirt Windex and clean them up all the time. So space-based solar power, giant solar satellites, microwave it down to the earth, makes a lot of sense. My favorite answer, due to David Criswell here, is you actually send technology to the moon. And in my version of saying this, we generate an artificial life force on the moon whose job is every day to go out there and generate new solar energy power plants and microwave it on down to us. And we just sit back sipping our mint juleps. And every year there's another terawatt of power coming down. And after a while, you can actually get rich again on this. And you can offload from the planet, from the biosphere, the entire responsibility of generating energy. That's a powerful idea. It started to get my juices going. I kind of feel like the early 60s again. We can do things. With these, particularly with solar and wind, there is a big problem in the erratic nature of it. You get plenty of power, but not times when you need it. And often you get it in places like the great western deserts. I mean, you fly over the western part of this country, or you look at a map, the planet is filled with deserts, and there's just nothing going on down there. Vast energy hitting there. If we put solar power plots down there, we can generate terawatts of power without displacing anybody. But it's not where the people live, and it's terawatts of power. You've got to get it from there over to places where we need it, and you've got to store it so that you can use it when the sun goes down. So I've been playing with this issue. About 6 weeks ago, we had an energy nanotechnology workshop at Rice, a magnificent conference over the week when we videotaped the whole conference. And I've watched the videotapes now 5 times. I've attended the conference 5 times over. I'm still learning things, the 5th time I've heard these things. And I've tried to come up with a picture for energy in 2050 that makes sense in view of all the things that I know, or think I know. And this is one possibility. There are many others. But imagine this. In 2050, we have, let's just take North America, a broadly distributed energy grid, electrical energy grid, where we have local energy storage and local energy regeneration from the stored energy and locally generating some energy from solar cells on the roof and other things that are available locally. And what I mean by local is allowed to change. It can be as small as your son's bedroom. It could be your house. It could be you and your neighbor. It could be your block. It could be your neighborhood. It could be your little small town. It could be your small business, business park. Or maybe you're in the business to provide local utilities. But that local place takes power from this grid, electrical grid, and stores it locally. And the electrical grid no longer has to be very reliable because locally you get to decide how many days you're going to buffer yourself, and locally you get to decide what quality of energy that you're going to have and whether you're going to make hydrogen or do whatever else. You do it locally, which means you don't have a big investment. If you made a mistake, you go change it a bit. And you can have now free enterprise competing, innovations year after year, going and continually upgrading this and say, I don't think that the best answer for being local here is a different answer. And then, so the great advantage of this is now you're not storing a hell of a lot of energy. You know, energy for a house is not a lot, and I can start using technologies that would never work on a vast scale. I can start using flywheels. I can start using batteries for my son's bedroom. And the great nanotechnology future, I'll bet you we can do batteries a heck of a lot better than we're doing now. The idea of storing a terawatt in one gigantic battery where you'd have to make a capital investment of, I don't know, $20 billion, and you'd almost certainly be wrong, is not very attractive. But doing it in 100 million times in little local places makes a lot of sense to me. And this all works if the electrical energy, if we can slosh power energy back and forth as electricity. So instead of transporting power as matter, coal in railroad cars, or oil in pipelines, or gas, natural gas in pipelines, or gasoline, we transport it as energy in the electrical energy grid. That still is not good enough because there's only so much power you can generate locally in these things. I mean, your house, you can put photocells on the top of your house, and maybe some days you can get enough power in Houston, and sometimes in Colorado you can do that. But that's not going to satisfy the needs for tens of terawatts for the planet. You need mass primary power. For that, we need to go to things like wind and solar terrestrial and solar in space and so forth, places where it isn't going to be available. They'll have really big peaks sometimes and other peaks. And now if a good fraction of all the world's energy needs comes from here, let's say 20 terawatts, you've got to slosh 20 terawatts around over thousands of mile distance, and you got to store it. Well, if we could get the wires to do this, and we can get the local storage, now it starts to make sense to me. So this is one thought that I have. And of course, it doesn't. We still have to get rid of gasoline, and I think hydrogen is the answer. I'm not going to belabor that point. But I just bring this up that I've been given this talk time and time, and it evolves every time, and up through about January, my best friend who listened to it said two things. One, too long, Rick, and too depressing. You know, we're just all looking at it. And so I'm looking, you know, they say, hey, where's the answer? So this actually is kind of attractive to me. The other aspect of this has to do with another event that's happening in science and engineering, which is our love affair with things on the nanometer scale, and seeing that actually a vast majority of what is the core of physical sciences, particularly chemistry and physics and material science and electrical engineering and computer and chemical engineering, is really the frontier of that is on the nanometer scale, to be able to build things on the nanometer scale as though it were a job in architecture, you know, an engineering thing. I'm going to put the atoms where I want to have a certain function. That we generally refer to as nanotechnology. And if you did it at the ultimate level of finesse, there wouldn't be a single atom in there in the wrong place. You could just do it, you know, with the greatest amount of parsimony that you could possibly do it. And I believe that it does, you know, once you get down to playing with matter at the ultimate level of finesse, almost as a tautology, you're doing things, you're answering problems to the extent that, to the best that is possible, governed by the rules of our universe. Of course, the great example of nanotechnology is all living things, the cells, the machinery of life is in fact incredibly perfect nanomachines. In many cases have been optimized by evolution to do their job with the greatest perfection that's possible. But they can't, biology in cells can't do everything. It can make your daughter, and it can make flowers and brains and eyeballs and so forth, but it cannot do electricity worth a darn. I mean, you have electric eels, you know, you can really get shocked, but that's not the kind of electricity that goes in a copper wire. It's ions moving across a membrane. You're never going to make a radio wave, a radio set, or a TV, or a laser by tinkering with the genome in some bacteria. You have to make things out of meat and bone, pretty much, because water is necessary. Whenever you try to make a metallic wire, it dissolves and reacts in the water. For that, we have another kind of nanotechnology. What I call the dry side, which is the art and science of building things without the machinery of life. And here we've got a whole array of magnificent things which tend to carry with them these things that are uniquely part of the dry side, the great strength like steel, the electrical conductivity of copper and superconductors, thermal conductivity of diamond, toughness, high temperature resistance. I mean, we don't build cars out of wood for a reason. Okay? We would build it for wood, out of wood, if in fact it were possible to make organisms prepare that sort of thing. And of course, this is the area where buckyballs and bucky tubes and so forth have their impact. So with this brave new world of nanotechnology and the incredible science and technology establishment worldwide, at this time when we need answers to energy, what are the sort of things that could be done? So since I've been, particularly in nano, I've been looking through this list, seeing what we could do. And top on the list is photovoltaics and photocatalytic reduction of CO2, taking a photon of light and somehow storing that energy. However that ends up being done in the ultimate, most perfect way, I guarantee you it will involve physics on a nanometer scale, because that's where the photon gets annihilated and created into an electron hole pair. The one goes over here and the other one goes over there, or it's some reduced form of hydrogen, or whatever catalytic thing. It's a nanoscale, and so when you almost, again, by a tautology, the optimum technology to do that will be a nanotechnology. What we have to do to make photovoltaics be able to do what I showed on that chart is we have to drop the cost of photovoltaics by somewhere between a factor of 10 and 100. A factor of 10 I can see happening. I don't know how we could do 100 without almost a miracle of nanotechnology. And yet I think it's possible, but not without massive, lucky research results. Fuel cells, to enable this distributed energy grid, to enable the hydrogen vehicle, we have got to solve the fuel cell problem. We have to drop the cost of fuel cells by a factor of 10 to 50. They're just too darn expensive, just way too expensive. And we have to get the platinum either completely out of them or mostly out. There's just not enough platinum in the world if fuel cells are going to have the huge impact that we want. That technology has got to be nanotechnology that replaces the platinum, that drops the cost of the materials for the membranes, that separates things. It will be nano that drives that. The hydrogen storage problem probably has no answer that isn't just pressurized tanks or liquid hydrogen. The search for material X, this magic sponge that absorbs hydrogen and turns it into a fuel of the density of gasoline, I think is a futile search. I mean, it's got to be some atom to which you stick the hydrogens. Carbon's one of the lightest ones. You have to stick a bunch of hydrogens onto it. You've just defined gasoline. But pressurized tanks aren't that bad, and liquid hydrogen's not that bad, and with new materials we can make it a lot better. Those new materials will come out of nanotechnology. Batteries, supercapacitors, flywheels, my favorite energy storage mechanism. To take that from where they are and make it in 10 to 15, 20 years to be the sort of thing that we need to store terawatts of power every day economically. Materials, materials, materials. You got to make stuff. You got to also somehow find the most efficient possible way of taking electrical power from Arizona to New York to do that electrical power grid. So for decades, we have been fascinated with high-temperature superconductors and thinking they may give us an answer. There is an alternative answer here, which I call quantum wires, that I'll talk about more tomorrow, coming from my favorite thing, the Bucky tubes, where electrons move down individual tubes as a quantized particle in a single transmission mode, every bit like a photon moves down a single mode optic fiber. There's just one transmission mode, and that's the way it's doing. And these tubes are small enough that the wavelength of the electron just barely fits in the tube, and there's only one way to do it, going down. So the normal mechanism of resistance in a normal metal, the electron's heading down this way, and it hits a vibrational lattice and goes off to the side, and after a while it's had so many hits you don't know where it's going, and so it just sort of diffuses down the wire and only goes that way because we put a voltage difference. That's the essence of resistance in a wire. That mechanism is gone for these Bucky tubes, gone. It can't be kicked to the side by a phonon, by a vibration, because there is no side. It's just going right on down. The only problem is how to get it from one tube to the other, and the answer to that is resonant quantum tunneling. It tunnels to the adjacent tube that's identical to it. It's made of carbon, it has a density of 1/6 of copper. We can spin it in a continuous fiber with all the tubes perfectly aligned, 6 around every one, out of 100% sulfuric acid, just like Kevlar. If we can make these things cheaply, like the polymer that it is in its essence to be, like polypropylene, we could rewire the electrical energy grid. And every place that you couldn't make the conductor any bigger than this because it got too heavy and sagging in here, now you can make it this big. Quantum wires. I think there are wonderful answers out there if we really go out boldly to get them. Nanoelectronics and computers and memories and so forth. Actually, a tremendous amount of our power is being consumed by things like this these days that plugged in. And if we can continue Moore's law for another 2 decades, as Ray Kurzweil, I think, rightly says, you'll be able to buy a computer for $1,000 that has the processing capacity of a human brain. Now, it'll probably be a very stupid human brain. You might actually have to send it to school for a decade like we send our kids to school. But at some point, as computers get to be more and more powerful in small size, robots will start to know where the heck they are. And when robots start to do that, you can actually start using robotic forces for these huge distributed energy systems on the Earth and in space. Would be tremendously enabling. Super strong, lightweight materials. Things dramatically stronger than steel, lightweight, that you can make cheap. That's all nanotechnology. If we're going to make flywheel strong, if we're going to take the mass out of automobiles, if we're going to make it possible to make buildings much stronger and simpler, airplanes lighter and so forth, where is that stuff going to come from? Nanotechnology. Anyway, I think I've made my point. One more heavy point, and then I'll let you go. So the vast majority of where I think the future to answering the world's most important single problem in our lifetime has got to come from the physical sciences and engineering. It turns out that the PhD production of physical sciences and engineering in our country is like the soft underbelly of our technology base. We're going terrifically in biotech and life sciences. No other nation is likely to surpass us anytime soon in that. And information technologies, we are premier. And once again, and that's where mostly our brightest kids have gone. In physics and chemistry, material science, electrical engineering, computer science in the sense of making computers, the stuff, and chemical engineering, those PhD sets, it's not a very happy story. This is the history of physics production in the United States, where you can see the big effect of Sputnik here with the peak right in the mid-60s. Looks like it recovered a bit lately, except that if you look at the fraction of those PhDs that are US citizens, that's the blue line, and it's been sort of level and falling off. If you plot it on a relevant scale, you compare it to GDP. After all, the physical science and engineering are the basis of the technology that makes all the Fortune 500 companies. In fact, pretty much all the companies. That's where their innovations come from. I mean, they, by and large, businesses make things. Or they make software that operates on the things that are made by others. And that technology base, of course, has grown dramatically in the past 50 years. So if you ratio PhD production in physics, and it's true for all physical science and engineering, versus GDP, you see very vividly where that Sputnik generation came. And those people look like me. They don't have much hair, they have gray hair. Many of them are still doing science, but most of you in the audience were either directly affected by the romance of space and Sputnik or by second order in your fathers and your parents. That was a terrific event. We need something like that again. More recently, in the past 20 years or so, here's the US production of PhDs, pretty well a flat line. What's really happening over the last decade is that Asian PhD production in physical sciences is growing up really dramatically. It used to be this is all in US institutions by and large, but now it's not true anymore. Over half of these Asian PhDs are now being granted in Asia, and most of those kids don't have to come over here to learn how to do science, particularly nanotechnology. You can do that. You don't need a superconducting supercollider to do it. Fascinating. Particularly the past 15 years, we've known this is a problem. The NSF has poured major resources in it. All of us have been involved in K through 12 outreach, all sorts of things. Get our American boys and girls into the sciences. That's what the effect of all that has been. The blue line there. I mean, if this were a company, if the U.S. this is some merit, a figure of merit of the company, and your company was the blue company and your competition is the red company, you'd have a little meeting. you would say, well, we have to fire this management, put in new management, tell the new management, study everything that you've done in the past. That's an example of what's not good enough. You got to do something different. And I think there's actually been only one time we've ever hacked this problem, and that was in 1961 with the Apollo program and Sputnik. And so I find an interesting coincidence of at least two critical problems. One is the energy problem, and the other is the persistent problem of getting kids into physical science and engineering. It's not just the energy problem. Physical science is the basis of not only our current technology, but the future technology. Not to mention national security. I believe that energy for 10 billion people is the biggest single problem that we face today. At minimum, we need 10 terawatts. Maybe we can do efficiency, we don't need any other, but let's not hold our breath with that. Let's go get 10 terawatts, let's get the technology to do it. Maybe we won't need it. And we have to have that installed and in place by 2050. For worldwide peace and prosperity, it has to be cheap. And I believe you simply cannot do it with current technology. I've been studying this for a year. I just don't see it, not cheaply, not worldwide, with what we've got now. In order to get that, we need boys and girls to enter the physical science and engineering in a way that they haven't since Sputnik. I think we can inspire them with a sense of mission. It sounds corny, but I think it's really, really true. Be a scientist, save the world. You know, if we can handle the problem of 10 billion people, we can give the technology to enable the prosperity of those 10 billion people, that's the problem. It's unlikely that we're going to go above 10 billion. But that's the problem of this generation. And we need to sustain them with a program, a Apollo-level program that has the romance of it. It turns out if you're really going to be innovating the biggest enterprise on the planet, money actually is not the problem. And this is an indication you can nickel and dime this problem. Just give me a nickel for every gallon of gasoline and jet fuel and fuel oil. In the United States alone, that's $10 billion every year. Okay, now go to a gasoline station and watch the SUVs coming in and tell me life's going to be different if the gas price is 5 cents higher. Of course we can afford it. I think it would be politically popular to do it. All we have to do is get the president to say, let's do it, and I think that money will appear. $10 billion is a tiny amount of money in the energy business. But if you pour it into frontier research, it is transforming. Take all the NSF, all the DOE, really frontier research. It's only a couple $100 million right now. We'd have a hard time spending $10 billion. I'm sure as soon as there's a sense of money, there will be plenty of people that will tell you how to spend that, and we'll have a giant problem to keep any of it for really frontier research. So I wonder, what is it that we're waiting for here? Are we waiting for an energy crisis to teach us that now we have to go do this? I mean, any energy crisis I can imagine us having will be deniable. We'll just say, well, that's a little hiccup, having to do with that local thing, and it'll be okay. Are we waiting for a global warming disaster? Well, short of the Gulf Stream deciding it no longer wants to go up to the UK, it's hard for me to imagine one that isn't deniable. Talking to people, on both sides of this, it's very much like the abortion debate. People have pretty well set their little feet in the ground, particularly in the U.S., particularly with the current political climate. Are we waiting for a new administration? Probably we're not going to get one, and what makes us think the next administration is going to be any better than this one? In fact, I kind of like the way the administration is responding, and the hydrogen issue, and the way that the DOE is really responding to the energy issue. I think we can handle it with the current administration. Are we waiting for an Asian technology boom to realize that we really have to solve this problem, American boys and girls, and getting the single most important enterprise? Well, I guarantee you we're going to have it. But it takes 20 years or so to build a scientist. It was that fear of technological inferiority that really triggered the Apollo thing. I mean, Kennedy, it was some combination of an inspired guess and just dumb luck, the Apollo program. But it's clear that's where things were going, because we were just scared, rightfully, to our core about our technological. It wasn't the fact that the Russians got their satellite up first, it's that they kept on getting them up while our things were blowing up the pad. So what we're waiting for is really leadership, but it can't really be an individual. What we're really waiting for is consensus, I think. And so, that's why I've been giving these talks, and I encourage other people to go around, just talk about this issue and how big it is. So thank you for your attention. I always throw up a slide of my favorite reading materials. Those of you who have access to the web tonight, I strongly urge that you go to see Amory Levin's most recent paper on hydrogen. I think it's a magnificent piece of work. No doubt there's a lot that's wrong in it, but I think it's one of the most penetrating analysis I've seen. And thank you for your attention.